Your homework is exercises on the second derivative. By the end of this lesson, all of these will make sense. We have most of this in place, but we'll finish today in a second. But first, this homework is taken from Rogowski, second derivative chapter. It's a college textbook that they use at Mines. It's a good book. So these are the problems I want you to do. Highlight these or circle these. In the first hand column, numbers 1, 2, 3, 7, 11, and 15. In the second hand column, I chopped off some things, so you have to do some writing. In the second hand column, first at the top of that graph, would you put number 20 and say, if this is the F graph, where are the inflection points and intervals where F is concave down? After that, also do 21, 21, 22, 23. 24 is getting to the idea, the real world idea of inflection points, where it's a point of diminishing returns. 25, 35, and 37. And in the far right hand column, would you highlight or circle as to do what looks like 9, but I believe is actually 40 or 39, 13, or really 43, 47, it looks like 7, and 51, and then 54 and 55. Those are the ones off that sheet that I expect you to do. Please do your work on another paper. All right. Now then, today's second topic, if I will, this will delete. Okay, today's second topic is another use of the second derivative. So, it's to test for extrema. We have the first derivative test for extrema. Remember, the first derivative test is to show that if the sign of the first derivative goes negative to positive before and after, so you're testing intervals before and after in a sign testing region, then that indicates that F has a min. If F prime goes positive to negative around a critical number, then F has a max. The first derivative test always works. In that, I kind of compare it to the quadratic formula. It's not always the easiest, but it always works. The second derivative test, I kind of compare to factoring. It's easier to use in a lot of ways, but it doesn't always work. It only works in cases where the derivative is 0, not where the derivative is undefined. It doesn't find mins at corners and cusps, or it doesn't test around vertical tangents. So it's limited in that sense, but it's also a very useful test. In a lot of cases, it's the one that's going to work best, especially implicit, you'll see. So it goes like this. To introduce the idea or the thought process behind it, imagine a little picture. Say at a certain point on the graph, a function had a derivative that was 0. Now that would indicate that the graph went flat there. And the second derivative is positive. Now remember, second derivative is changing the first derivative. So that means F prime is increasing. So the F slopes are increasing. And when you do that, you get this caving up shape. Now the combination of flat with concave up ensures a minimum. So with those two combined, it must be both, that gets a minimum. If you have flat with slopes decreasing or concave down, flat at an instant and concave down at that instant, you get a max. Now the justification has to be worded just right, just like the first derivative test. You have to say things well. You have to have subjects clearly defined. It's not it, or don't say F prime has a min when you imply that, when you really mean that F has a min, or F double is concave up when you really mean f double is negative. There's all these different ways that people make errors saying it, so make sure you pay attention to the justification. And if you have the first derivative 0 and the second derivative less than 0, I encourage you, instead of just memorizing this stuff, imagine the concept of the picture. This is saying flat with concave down, then f will have a relative maximum. If the derivative is 0 and the second derivative is positive, that's flat with concave up, f has a relative minimum. You show those two pieces of evidence happen at the point. All the second derivative is at the point, not intervals around the point. That's one big difference between the first and the second derivative. You don't do sign testing in the second derivative test. You're always putting a critical number into the derivative or into the second derivative and seeing what happens. Okay, so I have no idea why that's not going out. But it's computer's a little frozen apparently. But hey, we'll make it work. Okay, sorry about the delay. Here we go. So let's talk about what this looks like in action, maybe. If you want to find relative extreme by the second derivative test, the first thing you're going to do is find where's the graph go flat by saying where's the derivative equal 0. After we have that point, then we find the sign of the second derivative at the points we find, and then we make our conclusions. So that's the process. Here goes. The derivative is x squared plus 2x minus 15, which equals 0, and we set it equal to 0 to find where the graph goes flat. Solving this, we find that we have the graph going flat or horizontal tangents at -5 and 3. Right? Now, rather than set up intervals like we would on the first derivative test, now we're going to go to the second derivative test to see what's going on at those points. The second derivative is 2x plus 2. Now let's see what's going on at -5. If I put -5 into the second derivative, by doing so, that'll tell me if the slopes are increasing or decreasing at that point, and so if it's concave up or down at that point, and I'll be able to say what's happening at -5. Well, if I put that in, I get -8. That obviously is less than 0. So we've found a place where the graph is flat, and because the second derivative is negative, it's concave down. Well, we must have a min there. Now, if you have the cube shape in mind, that the cube has a min, or I'm sorry, a max rather, at the lesser x value, that's totally logical. So here's our conclusion, and then we'll jump to the other point, which will be a min. It goes something like this. You're trying to really restate the premise of the second derivative test, and that is something like f, not it, not f prime, not f double. F has a max at x equal -5. Now notice I'm just saying the x value because of the question. The question says find the x value. So I'm just going with the x. I don't need the y value. F has a max at x equal -5 because f prime at -5 is 0, and f double at -5 is less than 0 or negative. That's how the second derivative test reads. That's the evidence I should cite, citing that I'm satisfying the theorem. I don't want you to, although it's good to have in your mind, the curve is flat and concave down there. That's not the evidence you cite. The evidence is for the second derivative test. You cite the second derivative. You say the second derivative is negative, not it's concave down, not f prime is concave down. No concave down. The second derivative is your evidence. Okay? And as far as the other critical number 3, f double at 3 is, here's f double, positive 8. Which surely, because that's positive, implies the curve is concave up, combined with the flat spot we got from the first derivative, means we have a min. So our conclusion is f has a min, a relative min. at x equals 3 because f prime at 3 equals 0 and f double at 3 is greater than 0. So that's the evidence for the second derivative test. That's what it looks like. Hopefully that's how you did. All right. This board is not responding. Okay, so try the second problem with the second derivative test and see how it goes. Go ahead and pause right now if you want to try that. I'm going to roll in. First, find the graph goes flat. 2x plus 2, the graph goes flat at negative 1. The second derivative is just 2. Now, 2 is greater than 0 all the time, which implies it's always concave up. Now, if you think about the shape, that makes sense. It's a parabola opening up, so that it's always concave up is logical. So our conclusion, we have concave up with flat, which makes a minimum. We say f, not it, not f prime, not f double. F has a min at x equal negative 1 because f prime changes. Nope, that's the first derivative test. Because f prime at negative 1 is 0 and f double at negative 1 is greater than 0. There we go. There's the conclusion to the second derivative test. With that, then, you should be able to prove mins and maxes with two different methods, first or second derivative test. I will go back and cite one piece of, oops, where is it? One more thing. If you get f prime is undefined at a point, then if you plow ahead and try and find or prove an extrema with the second derivative test, you'll run into problems. Basically, the idea is that if the derivative doesn't exist, then the second derivative doesn't exist there either. And so it's hard to say anything about the sign of the second derivative when the point doesn't exist. If that happens, then the second derivative test fails. In that event, then you go back and use the first derivative test, which always works. Okay. That should do it. That should get you going, and you should be okay on that homework. I will post the assignment itself to my website and a key, and you can check your work. Have a good day.